morning, Professor Mike Hall. I'm pleased and honored to have a conversation with you about your science. So let me first introduce myself for the people who are going to listen to this video. So my name is Alain Fischer. I'm a physician scientist working in Paris in the field of immunology, and I'm presently the president of the Académie des Sciences. So Mike Hall is here today in Paris, coming from Basel, because he's going to receive this afternoon the very prestigious Grande Médaille from the Académie des Sciences, which is the most prestigious prize of the French Academy. So Mike Hall is a biologist. He trained in the US. Please correct me if I'm wrong. And then after some studies he performed in the US in molecular biology, genetics of bacteria. He came to Basel, Switzerland, at the University of Basel in the Biozentrum, which is a prestigious basic research institution where he did most of his career. And the reason why he is celebrated today, and among many other celebrations, by the way, is the fact that he discovered a major molecular pathway in cell biology, that is the pathway related to the so-called mTor molecules. He will tell us, I'm sure you're going to tell us about it, and that are governing, completely controlling, kind of conductor in cells of cell growth, basically. So perhaps, if I may start with the first question, Mike, you started by studying yeast and studying the effect of a molecule, a drug, rapamycin, and this is how you went to discover the mTor. So could you tell us why you were interested, one, in the model of yeast, and two, in studying the effect of rapamycin?
Well, first of all, hello, Alain. It's a pleasure to be here. Why did I start studying rapamycin, and why did I start studying yeast? And I suppose the question is, why did I study rapamycin in yeast? And the reason this is a good question is because rapamycin, for those who do not know what this is a natural molecule secreted by soil bacterium. And this bacterium came from a soil sample collected in Easter Island known as Rapa Nui, and this is why this molecule is called rapamycin. And this was an important molecule because whereas it was originally being developed as an antifungal, scientists isolated looking for a novel antifungal. As they were developing it as an antifungal, it had antifungal activity, but they found it had an undesirable secondary activity, and that was to suppress the immune system. So it was discarded. It was not further developed as an antifungal because, of course, suppressing the immune system is the last thing you want to do to someone with a fungal infection. But years later, as transplantation surgery became a viable medical procedure, it became such a viable procedure due to the discovery of immunosuppressive drugs. So if you had an organ transplantation, for example, in 1980, your chances of survival were, let's say, 20%. If you have an organ transplant right today, your chances of survival are, let's say, 80%, much better. And this is thanks to these novel immunosuppressive drugs and two courageous transplantation surgeons who developed immunosuppression. This was a revolution in medicine at that time, occurred in the 80s and 90s. So rapamycin was getting a great deal of attention then by this stage because it allowed transplantation surgery. We were working in Basel, near where there are two major pharma companies. One of them was at that time called Sandoz, now called Novartis. And one of the so-called blockbuster drugs of Sandoz was an immunosuppressive drug called cyclosporin A, or Sandimune, I think was its clinical name. So They were interested in understanding how this new one called rapamycin worked. And I was not working in this pharmaceutical company, but I had many friends who were, Basel is a very small town. In my laboratory, there was a postdoc by the name of Joe Heitman who was working on a project that was at the core, at the central theme of my laboratory at the time. And his project failed. And he'd heard about these immunosuppressive drugs because he was an MD PhD, so he had exposure to the medical literature. And he decided he wanted to understand how these drugs worked. Mm-hmm. So these drugs, these immunosuppressive drugs, despite the fact that they were responsible for this medical revolution, they were very effective. Nobody knew how they worked at the molecular level. So this is what captured his attention. So I introduced him to a friend of mine, who Raumova, who worked in the pharma company, who was interested also in understanding how these drugs worked. And they had the brilliant, albeit risky, idea to use yeast to elucidate the mechanism of action of this drug. Now this was a risky idea because, of course, this was a molecule that was being developed into a medicine to be used in humans, and to give it to a yeast cell, which is a unicellular, simple organism. It's what we use to make bread, wine, beer. To treat yeast with this, let's call it a drug. It wasn't officially a drug yet, but it was being developed into a drug. Was a very radical idea in those days. It was like giving aspirin to a yeast cell. Why would you ever do such a non-physiological thing? But what Joe and Rao remembered was that rapamycin was originally isolated as an antifungal, which is what yeast is. Yeast is a fungus. So they made the assumption, and this was where the risk was, that whatever the mechanism of this molecule, this mechanism was conserved all the way from yeast to human. That's the assumption they made. Okay, and of course, rapamycin evolved as a weapon in microbiological warfare. It's a bacterial product, and that's how the bacteria compete in their niche in the soil for nutrients. So they had the extremely bright idea, I think, to use yeast, and of course, I wouldn't be sitting here today if it didn't turn out to be a good idea. Another reason we chose to use yeast is that this is in the late 1980s, and at that time, we wanted to take a genetic approach to understand what the target is, and you could not do genetics in mammalian cells. You had to do a biochemical approach. But we wanted to use what we referred to in those days as the power of yeast genetics to elucidate the mechanism of action. And it was a very simple experiment. All we had to do was plate yeast cells on a petri dish in which we'd put some rapamycin and let spontaneous mutants grow up. And there we had the...
And the story started.
Yeah, that's where it started.
Yeah. So it went to be crucial and critical in defining a system based on these target of rapamycin molecules that govern growth. So did you recognize it immediately as something important, or did it come progressively? So how was the follow-up? So did all of your lab immediately jump to work on this, and still was it one of the projects among others?
I would say it was both of those things, because remember, we are setting out to elucidate the mechanism of action of rapamycin, a very interesting, exciting immunosuppressive drug.
Indeed.
And that we achieved. We discovered what the target of rapamycin is in the cell. We discovered the protein it binds, and that protein turned out to be a novel kinase, protein kinase, which when rapamycin bound it, it inhibited that kinase activity. So our first goal had been achieved. We discovered how how this immunosuppressive drug worked. And we published this in a very, very good journal. Mm-hmm. So, yes, we were very excited about our discovery. It was something we were clearly excited about. And in fact, the project almost died at that point in the lab because we achieved what we wanted to achieve. Joe Heitman had to go back to America mm-hmm. to finish medical school, and the rest of the lab had their own projects. But then another student in the lab, her project failed too. And at that point, I told her, or I suggested to her that she should go back and work on these so-called TOR mutants. Mm-hmm. So she ended up cloning the TOR genes. That's what revealed that these genes, which when mutated confer rapamycin resistance, that these genes encode kinases. So then the difficult part started because we had kinases. Yeah. We knew they were target rapamycin, but we had no idea what these kinases did in the cell other than sit there to be the target of rapamycin. And they clearly did not evolve to be the target of rapamycin. They had some other function.
For sure.
So, and there the story gets a little convoluted. It was a long and dark, winding path to get to the end, because we had one observation: if we knocked out the TOR genes or treated the cells with rapamycin, in other words, inhibited TOR, the cells arrested in the cell cycle, a specific phase of the cell cycle. And in those days, the cell cycle research field was a blossoming field. It was a very large competitive field, led by people like Paul Nurse and Lee Hartwell, people we all know very, very well. And when we saw this cell cycle arrest at a specific phase of the cell cycle, phase called G1, we thought we had discovered a new mechanism to control cell cycle, in other words, cell division. And after this initial observation, then we did many more experiments to try to understand what role our TOR kinase played in cell cycle control. And everything failed. And this went on for years. Because I don't have enough time to tell the whole story, we eventually decided, largely because we'd eliminated all possibilities, that maybe it didn't control cell cycle, cell division, but it controlled cell growth. This is perhaps the achievement in my lab which I am most proud of, making this realization. And the reason for that is that cell growth was not thought to be regulated in those days. It was thought to be a passively controlled process. In other words, if you gave nutrients to cells, they had building blocks, and they built and they divided. They grew and divided. But there was no active mechanism to control the cell growth process, like there's an active mechanism to control the cell division process. It's very odd looking back at it from the perspective of today, because one could say that cell growth and division, they go hand in hand. And they are probably the most fundamental things a cell can do. It's probably the most fundamental behavior in cell biology. Yet everybody assumed that the growth part was a passive process, nothing to be studied there, and everybody's focusing on cell division. So when the light bulb finally went off that maybe cell growth is controlled, and if it is, maybe TOR is controlling the cell growth, is the central controller of cell growth, much like cyclin-dependent kinases are the central controllers of cell division. So once that light went off, then we understood everything a lot better. Or at least we started designing experiments which gave understandable answers now. We went from complete darkness into complete light. That was the magic moment that you were talking about later.
Yeah, great story. And interestingly enough, as I think it opened it happens very often in the past, failures in some research lead to great discovery and new concept, new paradigm.
Yeah, you have to have a very thick skin sometimes, I can assure you.
For sure.
Yeah.
That's a lesson for young people. And so that's your own story. So what about the reaction of the scientific community? Did they buy your discovery rapidly, or were there some controversies, or how it went?
No, they did not buy it. And the reason they did not buy it, there were two reasons, I would say. One is that nobody thought cell growth was controlled. So they refused to accept. It was so ingrained that cell growth was not controlled, they didn't believe we discovered a controller of cell growth. And the other problem was that if you go back to literature in the mid-1990s, and even much more recently than that, and you read a paper that has growth in it, cell growth, it refers to the cell cycle, cell division, which is an increase in cell number. It's an understandable description of cell division. A cell goes from 1 to 2. There's a growth process there. But what we discovered is not increase in cell number, but increase in cell size or mass. So what we first had to do was convince the community that the word growth had been misused up until that point. We were not studying cell division like we ourselves had thought in the beginning, but in fact we're studying cell growth. And this is then what started what I would say the field of cell growth control. Once they understood, we're not working on growth as they think, based on what they think it means, and that cell growth is, in the new definition, is actually an actively controlled process. Once those two concepts were accepted, then things went very smooth.
So today we are more than 35 years later. So the field has grown exponentially, I would say, with the complexity of the system is quite huge. I don't think we have time to go into all of the details. And it happens also that it has some medical applications up to cancer. So perhaps would you tell us a little bit of what are today your centers of interest in the development of this field?
It's true. Since that first paper that mentions TOR in the literature in 1991 from our laboratory, someone told me recently there are now more than 7,000 papers per year in the TOR field. So this is an exponential increase in publications, an exponential increase in complexity of the biology. And what's driven that is the fact that TOR turned out to be not only fundamentally important, like I just described, mediating cell growth, but it all turned out to be clinically important, medically important, because defective TOR signaling is the basis of many disorders, which I'll tell you about in a moment. And that, of course, then triggered a lot of interest in the pharma industry. So we have three large communities: the basic research community, the medical community, and the pharmaceutical community, extremely interested in TOR. So this was a good thing for us. Our knowledge of our work spread, but at the same time, it became an extremely competitive field at the same time. So the diseases that TOR is implicated in, as you might imagine, cell growth is a very central process. And if it becomes dysregulated any way, there can be pathology associated with that. I'll start with the most common case of dysregulated TOR, and that is cancer. As we know, cancer is a disease where cells lose cell growth control and they grow now out of control. They grow either at the wrong time or in the wrong place, and this, of course, gives rise to a tumor. And it's been shown that TOR it's been calculated that TOR is active and contributes to tumorigenicity in 80% of all cancers. It's understandable. It's at the central of the growth process, and TOR is a growth disease. There are other...
Still, if I can interrupt
Sure.
you, in that case, it means for cancer cells, there is a direct link between cell growth in terms of biomass and cell division.
That's right, but not only in cancer, but in normal physiology.
Of course, but not in all cells, as you know.
Yeah. You cannot dysregulate only TOR. I have not told you why when we inhibit TOR, important point I failed to mention, why is it when you inhibit TOR, you get a cell division defect when it's actually controlling growth? And the reason is that if you inhibit growth, you inhibit cell division indirectly, because cells know that if they've not grown large enough, they inhibit their division. So we were fooled by this indirect effect of TOR inhibition. So that solved that troubling issue we had from the very beginning. So there are a number of diseases. If you cardiac hypertrophy, for example, again a case of cells getting larger than they should be. In this case, in the heart. This is also due to defective TOR signaling. These are all cases of hyperactive TOR signaling. But there are cases where there's disease due to reduced TOR, decreased TOR signaling. For example, diabetes. Diabetes is TOR is a part of the insulin signaling pathway. And if you lose insulin sensitivity, you lose TOR activity, it can result in diabetes. And in fact, what all these diseases I've just mentioned have in common is that they're all age-related diseases. Which brings us to a new topic, which TOR was also shown about 20 years ago to be involved in controlling the aging process. And this opened up, again, a whole new area of study, created a great deal of excitement in the aging field.
It looks like mice that receive rapamycin, they do live longer. Yeah,
this was shown in 2009 that if you treat mice with rapamycin, you can extend the lifespan of mice by about 10%. This was the first ever pharmacological extension of lifespan in mammals. It had been shown already in yeast and in worms and in flies that inhibiting TOR could extend lifespan. And then it was shown in mammals in 2009.
So what about humans?
Humans, we don't know. We're looking for, well, I'm not looking, but if you'd like to volunteer for a study, I'm sure I will tell you, when this paper came out in 2009, many people started buying rapamycin and dosing themselves off-label, trying to extend their lives. Many people take, for example, also metformin. Metformin and rapamycin are the two drugs that people take. But the interesting thing about the discovery that rapamycin extends lifespan is that this observation also answered a puzzle which had existed since 1935, when it was shown that if you eat less, you live longer. It's what in the aging field they call dietary restriction or caloric restriction. And nobody understood the molecular basis of this until it was shown that inhibition of TOR extends lifespan. Because, as we'd shown earlier, TOR controls growth, increase in cell mass, in response to nutrients, among other stimuli. So if you treat with rapamycin, you inhibit TOR, you trick the cell into thinking that there are no nutrients. It doesn't sense them anymore. It can't respond to the nutrients. So rapamycin is the equivalent of eating less, or caloric dietary restriction. And this observation obviously suggests that the way dietary restriction extends lifespan is if you eat less, you have less TOR activity. And then this alters globally the metabolism of the cell in many ways, which we showed over the years. And altogether, there's a net beneficial effect which translates to longer life.
Broadening a little bit the discussion, So how do you think the future of life sciences? I mean, very often advances in life sciences come from breakthrough in technology. So do you foresee from where it will come for the next steps in research in life sciences?
Well, I think life sciences still has a long life ahead of it. There are still many things to be discovered. You're absolutely right. Advances in life sciences are made based on new technologies which are developed. Much more so today, I would say, than in earlier days, the days of Jacob Monod, for example, where all you needed was a toothpick and a petri dish.
That were the happy days. That were the happy days.
They were the happy days. There was more emphasis on concepts than on technology, which is a kind of science I miss, I have to say. I would not say I'm very technology-oriented. I'm more concept-oriented. But this is the way science goes. I think science is also becoming more applied. There's ever greater pressure to produce something that will benefit society, new drugs, new cancer drugs, new therapies, for example. So there's still a lot to be done, but it's changing. And of course, we have AI now. This is causing revolution as well in all aspects of science. I'm curious to see exactly how much impact that has, though. We're in exciting times.
Sure, for sure. So for a young person who wishes to go into research in life sciences, what would be your advice or your advices?
I would say go work in a laboratory, see what it's really like. And I would say this to anybody who wants to pursue any profession, not just science. Expose yourself to as much as possible to all the things that you think might interest you, to see what they're really like in a day-to-day way. Because science is, I should say, is not a profession for everybody, but if you are the type of person that would fit very well as a scientist, you'll be extremely, extremely happy. It's a very good profession if you are the right person for it.
Good to hear from you. And then to finish with, I have a bit more personal question. So you are kind of if I may call you that way, an atypical scientist in a way that you came from America, a little bit of South America, but mostly North America, to work in Europe. And unfortunately, the other trajectory is more frequent. So what made you to travel eastbound? And so what are the strengths of European research?
What made me come to Europe? It's true, I did my PhD and my major postdoc in the United States. But when it came time to look for a position where I would start my own lab, I looked in both the United States and Europe. In French-speaking Europe, in fact. And there are a couple reasons behind that. One is, I would say I was not a typical American postdoc in those days because I'd grown up outside of America. So I was more global to begin with. So I was more open to the outside world. Many Americans don't see beyond the borders of America. So I was more open to it. And I'd also and when I was a PhD student, I'd been doing bacterial genetics because Jacob and Monod were they're my heroes, my role models in how to do science. And when I finished my PhD studies, I had to travel to Paris, to the Pasteur in particular, because that was the kind of mecca for me in those days. I had to experience that, and I came to the Pasteur for 1 year just to be at the origin, at the source, before then going back to America to study another subject which I had planned in advance. And that was after that second trip back to the United States that I started looking for positions both in the U.S. And Europe. And there's one other important factor that plays into the story, is that during this almost 1 year I'd spent at the Pasteur, right after my PhD, I met the person who is now my wife.
Okay.
So this also opened me up.
That's a good reason.
That also opened me up to coming to Europe.
But still, you missed the French-speaking Europe by not a long distance.
Well, there's another story behind. There's another story behind that. I was discussing with different institutes in Paris and in Lausanne, French-speaking Switzerland, and I was then contacted by someone at the Biozentrum in Basel. And asked me if I would be interested in looking at a position there. Because it's true, it was rare that an American would be looking for a position in Europe, and word got around, there's this American looking for a position in Europe, and people wanted the American influence in their institutes. And the truth is, I could not have been less interested in a position in Basel. Basel had a reputation of being I would say, a gritty, industrial city. This was months after Chernobyl, which made all of Switzerland radioactive, essentially. It was also months after what's called the Schweizerhalle crisis, where one of the pharma companies' chemical waste tanks exploded and polluted the Rhine and killed everything in the Rhine. All reasons why I should not be interested in Basel. It was, in addition, of course, it wasn't French speaking, and it's not even normal German speaking. It's Schweizerdeutsch, Swiss German speaking. But the person who invited me, I admired, and he said, "Just come and look." And so I went and looked, and what I realized at the institute there, where I now work, seemed like an absolutely ideal place to get a career going. Everything seemed to work very nicely. They had a good pool of students, good pool of postdocs, good colleagues, good resources, good funding. All the conditions were perfect. I'd been to many places in the world up until that point, and I'd never seen all the conditions being right like that. So I decided, well, this is maybe a good place to get my independent career going, and then we can move somewhere else later. Then I had to convince my wife to go to the German-speaking Switzerland. We were living in California at this point, San Francisco, which is also a very nice place to live. And we decided we would go for 3 years, and if we liked it, or if they liked us, we would stay. If not, we would look somewhere else. By this time, I'd moved so many times, not only professionally, going across the Atlantic within America, but I'd also moved many times growing up as a child in South America. So moving was not a particularly stressful thing for me. So, but ironically, I moved to Basel and never moved again.
Yeah. Which is.
I settled down finally. Yeah.
So do you think there are enough such institutes in Europe these days, like the one in Basel? So what is your opinion about European research?
I don't think there are many. It's very hard to achieve this. Let's say it's not perfection, but let's use that word. Let's achieve that state. Let's say it's this enlightened state of being able to do science. There's always something missing, but they all seem to be there. And you might ask the question, why are they there? And why are they not somewhere else?
Exactly.
And I've thought about this, and I think the reason is it's not only centrally located in Europe, so nonetheless, it's not a beautiful place like Paris where you would want to live, at least back in those days. It's become a very nice city in the meantime. But I think the reason is we have to thank Switzerland for this, because Switzerland is a very famous country, of course. It does extremely well on an international level. It's in science, in banking, and in art, in all these, in many, many domains. It does not make sense. This is a very small, landlocked country with no natural resources. Why is Switzerland so successful? And the reason it's so successful is that politicians, I'm not exactly sure who, I've not been able to pinpoint this, have realized that the only way a small landlocked country with no natural resources can succeed is if they invest in the brain. In other words, they invest in education, research, and innovation. And that's what Switzerland has done. And that's what created the conditions that made and still makes my institute so good. And in fact, Switzerland in general is a good place to work.
So I think let's hope they will inspire our politicians in the neighboring countries to do the same.
Yes, that would be very nice, but the urgency is not there because you're blessed by so much beautiful natural resources that
still.
I always think of the opposite end of the spectrum as a country I grew up in is Venezuela. It was extremely petroleum rich.
Absolutely.
So they had so many natural resources, at least in this one resource, that they never bothered to develop anything else. They never, or Switzerland had no resources. They developed what is completely lacking in Venezuela today.
Okay, I think we'll stop here, if you don't mind. And thank you very much.
We could go on for hours
and hours. No, of course, but I think there are limitations. So thank you very much. So I think this was attractive. I hope, I'm sure, I not only hope that people will be interested to listen to your thoughts and your history, fantastic history. And again, congratulations for this Grande Médaille.
For the Médaille and for the interview. It was very pleasant.
Thank you.